This is a video for Lab 2 for Physics 1050, Acceleration Due to Gravity. In this lab, our primary objective is to try and measure the magnitude of the acceleration due to gravity, or G. We'll do that first with a falling ball. And then later on in the lab, we'll also find the acceleration of a falling balloon, and we'll see if it's very different from the ball, and we might think about why it's different from the ball. For your apparatus, you've got a Lab Pro, a motion sensor, its cord, 3 rods, 2 clamps, a ball, and a balloon. You'll probably have to inflate the balloon yourself. Let's get started on the assembly. So let's start by screwing the small rod into the back of the motion detector. Okay, and then we're going to attach that to a clamp. Might have to adjust the clamp a little bit to get it on there. There we go. Let's adjust it to a clamp. And then we're going to put that on the medium length rod. We'll get those screws nice and tight. We don't want things to fall off once we get them assembled. And then we're going to put another rod on here, another clamp on here. Get that on nice and tight. And we'll take our longest rod, screw that into the desktop. And then we'll attach this one. Get that on nice and tight there as well. Okay, so when we do this, what we want is to have everything on nice and secure, and we want the gold foil circle of the motion sensor pointed right at the tabletop. So that's what we want. The next thing we need to do is to plug the motion sensor into the Lab Pro. So let's take our cord and let's plug it into the port on the motion sensor. We'll keep that cord out of the way, and then we want to plug it into the Lab Pro. The port on the motion sensor is labeled DigSonic, so we'll look for the DigSonic port on the Lab Pro. Since this is the first thing we're plugging in, we'll put it into port 1. Okay, all connected. Next, what we want to do is open up our Logger Pro so that we can take our measurements. So we'll click on that, we'll say open. Oops, it didn't open. Sometimes the computers hiccup. If that happens, just double click on ball.cmbl in your folder. Okay, so if you've got the correct file open, then what you'll see is that you have 3 graphs on your file: position versus time, velocity versus time, acceleration versus time. Okay, now we have to get ready to use the motion sensor. In using the motion sensor, it's very important to know where the origin is. Where is y equals 0? And we're going to have the computer tell the motion sensor that the table is y equals 0. To do that, we click on the word experiment on the top of the screen, and we click the word 0. Should hear a click, click, click. That means it's been zeroed. Okay, now we're ready to collect our data. So what we do when we collect our data is we hold the ball under the gold foil circle. We hit collect, we wait till we hear the little clicky noise, then we drop it. Okay, it's hard to tell what my data really looks like. I'm going to press that A button for auto scale. This kind of looks okay, but not great. I'm going to try again. A little better, still not great. If this is happening to you, you may end up calling somebody over for help. We could try switching the setting on the inside of the motion sensor. Let's try again, see if that works a little better. Oh, we got it now. Okay, so if we look at my data, I've got, here's where I held it still, here's where I released it, it hit the table, bounced up, bounced down, bounce, bounce, bounce. This is good. I'm happy with my data. So next I have to analyze my data. Your lab is going to ask you some questions. For example, where did it first hit the table? Where is it moving up? Where is it moving down? Where is it at the top of the path? Questions like this. You can look at your graphs and answer those. Next, we're going to start to analyze our data. We should make sure we've got it auto-scaled properly. Now we can see everything. We're going to analyze these three graphs and use all three to tell us the magnitude of the acceleration due to gravity. We're going to try and find g. So let's get started on that process. I'm going to try and bring the camera in a little bit closer. If you get woozy with a moving camera, you can close your eyes for a moment. Okay, so my camera is in close to my computer screen now. Let's just get that propped in. Don't want it to fall on me. Okay, hopefully you can see that computer screen reasonably well at this point. Now let's get into our analysis. The lab instructions tell us to start with the position versus time graph, so we'll start there. It says highlight the first bump, so the time between T1 when it first hits the table and T2 when it second hits the table. So I've got that highlighted. And then it says to do a curve fit, so we'll click Analyze, Curve Fit. So it's doing a curve fit for this highlighted part. We'll ask, what's the form of this? This is a curve, looks like a quadratic for me. I'm gonna click on quadratic. Then I'm gonna choose Tri-Fit. That black line looks like it's going through my red line pretty well. I think that's a decent fit. Then I'll hit OK. All right, so this, I'm just gonna make the font a bit bigger so hopefully you can see it on the screen. Oh my goodness, mouse is sometimes hard to use. Move this over here. Okay, so this is my curve fit for this portion of the data, and my fitting parameters are shown right here with their uncertainties A, B, and C. How do we use this fit to find the acceleration due to gravity? Okay, the first thing we're gonna do is write down what the fit told us. So it says x equals to A times t squared plus B times t plus c. First thing I'm gonna do, x we typically use for horizontal motion, y we keep for vertical motion. I'm gonna say y is equal to a times t squared plus b times t plus c. Okay, here's our math equation. The next thing we wanna do to figure out what is the magnitude of the acceleration due to gravity is write down our physics equation. So I know a physics equation that looks like this. Y equals y0 plus v0t plus 1/2 at squared. Okay, what about this a? Well, I know a is the acceleration due to gravity. A is equal to minus 9.81 meters per second squared. So minus means down, acceleration points down. 9.81 meters per second squared, that's what we call g. It's the size of the acceleration due to gravity. It's always positive. A is equal to negative g. Okay, so I'm gonna fill in a is negative g, and then the other thing I'm gonna do is take this term and put it first. I'm gonna take y0 and put it last. Okay, so y is equal to 1/2 times minus g times t squared plus VOT, leave that one in the middle, plus YO. Okay, my very last step, I'm gonna haul that minus out front. Y equals minus 1/2 g t squared plus VOT plus YO. Okay, here's our physics equation. Right under that, I'm gonna write down our math equation. Y is equal to A times t squared plus B times t plus C. Okay, we're asked to find g, so let's compare these two equations. So the thing that's in front of t squared is minus 1/2 g, and the thing that's in front of t squared is a. So this tells me that a equals minus 1/2 g. Okay, so our parameter a should be negative 1/2 times g, which is 9.81. Our goal is going to be to find the value for g, so let's do a little cross multiplying. G is minus 2a. If we look at our computer, a is minus 4.886, so we'll put minus 4.886 here, and we'll come up with our value for g. So that's how we can find g from our first fit. We're also going to find g from our second fit. from our velocity versus time data. This one maybe you're a little more familiar with already. So let's come to our velocity versus time graph. So in your instructions, in this part you have to read very closely, it says highlight the linear portion of your graph between times t1 and t2. So t1 is probably about here, t2 is about here. We want to highlight just the linear part. Okay, that's really important. If you highlight beyond those points, you'll get a funny fit. So if we look at this, this looks linear. Let's do a linear fit. Analyze linear fit. That looks good. I'm going to turn on the uncertainty, and then I'm just going to make this font a little bigger so you can see it a little better on the video. Okay, now let's do our analysis for this one. Probably a little more familiar with this type of analysis. So our math equation says V equals M times T plus B. So there's our fitting equation, or our math. For our physics equation, V equals VO plus A times T. Again, A is negative G, negative for down, G for 9.81. I'm going to do a switcheroo on these terms. V equals A T plus VO. Then if we compare, we'll write our fitting equation right under here. V equals slope, M times T plus intercept. The thing in front of the T is our acceleration. The thing in front of the T is our slope. So we see that slope M equals our acceleration equals minus G. So G is equal to negative of our slope. Our slope is minus 9.822. G is negative of that, so we can find our slope. We can find our value of G this way on this graph. Okay, one more graph to look at. The last graph to analyze is our acceleration versus time graph. For this one, your instructions say to highlight the constant portion of the acceleration between times t1 and t2. t1's about here, t2 is about here, the constant bit is about here. So this is acceleration. It's more or less constant. So the thing we want here is the average value. For average, we find the mean. So we'll come to analyze and we'll choose statistics. Okay, I'm just gonna make this box a little bigger so we can see it. Okay. So if we think about this graph, we know that this part is showing us the average acceleration, the mean acceleration. So mean equals A equals minus G. So G is going to be the negative of the mean. And the mean is negative 9.866. So there you can find your G value. Little thing you might have forgotten about your uncertainty analysis. You'll want to find the uncertainty here. Your standard deviation is 0.3242, or whatever your computer tells you. You also know your sample number. So that's the number of points you've collected. The uncertainty is the standard deviation divided by the square root of the number of points. So that's a little tip for when you're finding your G here to find the uncertainty. The uncertainty is the standard error, which is this, the standard deviation, divided by the square root of the number of points. So that takes you through the heart of the analysis for the falling ball. You'll repeat the experiment for the falling balloon and then find the acceleration of the balloon, and you'll see, is it equal to G or is it different